Okay. So yabancı misafirler vardır diye düşünüp İngilizce sunum yapmayı düşündüm. My talk is about the enhanced supply chain resilience in nuclear power. In my talk, I have several headings. First of all, the meaning of resilient nuclear supply chain, expansion of nuclear power nowadays, structure and characteristics of nuclear supply chain, obstacles and opportunities, future challenges, and there is an important topic also, nuclear fuel supply for the coming years that has to be mentioned a bit, and finally, expectations for the future. Okay, when we talk about resilient supply chain, the characteristics of that kind of supply chain to be resistance for shocks, changes, and easy to recover, so that we'll have some kind of robustness and also elasticity, flexibility for the operation of the supply chain. While in case of nuclear supply chain, this is a necessity because there are ups and downs in the past, as we experienced earlier. One of the speakers earlier mentioned about the situation 10 years ago. So there was a nuclear renaissance, but it didn't finalized, unfortunately. But this time, situation is a bit different. Probably because of the climate change, nuclear is expected role in the future in order to compensate the energy need. So ability to respond quickly against disruptions and by proper contingency planning, so that we have to consider some kind of unexpected situations and get ready and make an action plan for that kind of situation. And the aim is design a competitive and resilient supply chain, serve new build projects as well as long-term safe operation. Nowadays, new reactors are expected to serve for 60 years. So this is a long time. So we have to arrange ourselves for that kind of extended operation and enable knowledge transfer, especially members of supply chains should exchange information in order to make a better competency in the field. Safety culture is an important item, and this has to be disseminated throughout the supply chain. For every member of the supply chain should establish a solid safety culture within the entity, and for the all workers should have that kind of insight for the nuclear energy. And quality management is an essential part of the supply chain. So this is not only a responsibility of a single company, but also the whole supply chain. Okay, nowadays there is a significant tendency towards nuclear energy. We see that in almost every corner of the world. Existing nuclear fleet is aging. This is one problem. But on the other hand, there is a new tendency for small modular reactors. This is a relatively new concept, but this is not a new idea. If you look at the development of nuclear energy in the past, there were certain examples of small reactors operated for many years. But due to the climate change, in order to mitigate climate change, nuclear energy has a significant role from now on, and most of the countries consider including nuclear into their energy mix, whether they are already using nuclear or a newcomer country. And there are different expectations. IAEA considers 50 to 80% growth in nuclear generation. There are other more optimistic expectations. I'm not going to talk about them, but if you consider them, there will be a new nuclear reactor in every corner, almost. So this is probably not possible to accomplish, but still wide dissemination is expected. Currently, 31 countries, in addition to 25 countries expected to triple the generation by nuclear. This year in COP29, there are 6 more additions, including our country, so that most of them are existing nuclear users, but some countries are not using nuclear yet, but they are considering to include significant amount of nuclear generation in their energy mix. And mostly US, Europe, and Asia, probably these regions will be the important users for nuclear in the future. China is a significant developer and user. Just to give you an information, they include new generation, nuclear generation capacity in every year, just the amount of our total capacity in Turkey. So this shows the significance of nuclear in China. But not only such countries, but also developing countries, especially countries in Africa, they consider nuclear, Kenya, Ghana, and there are many other countries. So they are looking forward to have nuclear reactors in their country. Of course, we are talking about SMRs, but in addition to SMRs, large units will be instrumental in the electricity generation, so that they have different roles. Maybe SMRs are more operable for small units next to the an industrial facility, but large units will serve as electricity generator solely, so that they have room for all kind of nuclear power plants in the future. SMRs, in addition to electricity generation, industrial processing, desalination, hydrogen production, they consider these kind of non-electrical applications in their scope, so that they create kind of attractiveness for the industrial companies. Just to give an idea, estimated value for international procurement in nuclear is expected to be $26 billion per year around this time of the year. In the future, I expect that number might be increasing due to the extension of the nuclear energy utilization in the world. It's interesting, Sweden, they have used nuclear in the past, but there was a nuclear moratorium several decades ago. Similarly, Italy, they never had a nuclear power plant in their country, but now they are considering nuclear, and they try to establish a nuclear supply chain in their country. Currently, they support other countries providing manufacturing activities in their country, but they want to install nuclear power plants in their country. UK similarly. So they are like in ENERJİ, so that nuclear is considered to be an option. And these are new builds, and they have to replace existing aging fleet. So this will create another market for the nuclear reactors. Next one, please. Well, when we talk about nuclear supply chain, this is really an extended network between companies. If you look at the structure of that pyramid, at the top, technology vendor company exists. This is the technology developer, and they work with system integrators, original equipment manufacturers, sub-component suppliers and distributors, processors and fabricators, raw material supplier, and miners. So they make the supply chain pyramid. And of course, all kind of materials, all kind of manufacturing activities will be needed in order to accomplish that complex work. When we look at the important items in the nuclear power plants, nuclear steam supply system, reactor pressure vessel, rod cluster control assembly, control rods, complex alloys, other structural materials, buildings, pumps, vanes, valves, all kind of equipment will be necessary in order to complete a nuclear power plant construction project. Of course, they are the combination of many raw materials and intermediary materials and different kind of manufacturing processes, casting, forging, extrusion, all kind of manufacturing processes will be involved in the process. Once we talk about the nuclear supply chain, we consider all kind of products, equipment, devices, and also all kind of services, especially during the maintenance outages. There are significant amount of work, usually done by several thousand people working all together. And usually nuclear supply chain is called global, but for new build projects, if they have government funding in most countries require local involvement other than international manufacturing. But this is not necessary, but certain countries impose that restriction. And certain items, as I mentioned earlier, requires design and manufacturing certification. Recently, for the last maybe 15 years, there was a standard developed by ESME, nuclear quality assurance, and it covers all the life cycle from design, construction, operation, and decommissioning. And most of the nuclear supply chain companies consider that standard is a not requirement, but necessity in their operations. And this is usually the reflection of the work done in the company, so that it supports the activities. So if you consider a typical nuclear reactor, Gen 3, Gen 4, these are a bit large sized reactors. Typical consumed materials are listed here. Concrete, about 6,000 cubic meters. Steel, about 61,000 tons. Forgings, 4,000 tons. Probably that includes pressure vessel. 200 pumps, about 5,000 and more valves, 210 kilometers approximately piping, 2,000 kilometers cabling, and over 50,000 welding seams. So if you consider these numbers, you are appreciating the extension of the work, the context of the work. So this is really a huge project. Among them, we also have some nuclear grade materials. In order to have that kind of label, materials should be in contact with the primary circuit in the nuclear power plant, emergency cooling system, and direct safety related equipment. And in order to manufacture this kind of materials, companies should have a special certification, and safety related items also need additional performance testing requirements. Significantly safety label containing equipment should assure the performance, reasonable performance of the equipment in order to be employed in the power plant. Next one. In the nuclear supply chain, in certain countries like the US, Spain, Germany is kind of out, Russia, Japan, China, they have very well established nuclear supply chain in their countries. Czech Republic, Czechia is also another country. They have almost all kinds of activities within their country. And there are certain vendor companies, names are familiar to people within that community: Framatome, Westinghouse, Rosatom, SMPTC, General Electric, Mitsubishi, Hitachi. There may be some others, but still these companies, huge conglomerate companies involved in the development of nuclear reactor design and all the system. Codes and standards are quite important here. There are different type of codes and standards. I only listed several of them widely used. One is ASME pressure vessel and pipes codes, especially primary circuit materials. You have to have that kind of certification. In France, RCCM and RCCE, one is for mechanical components, the other one is for electrical components. This is also another internationally accepted design and manufacturing certification, so that newcomers should consider these, but also there is also another effort to harmonize this kind of codes and standards internationally and to come up with a unified version in the future. Probably that will be realized within the next 5 years or so, so that new reactors will follow these standards. There are also new manufacturing methodologies: additive manufacturing, diffusion bonding, electron beam welding, diode laser cladding. Since nuclear industry is so conservative, it's not easy to adapt these practices readily in nuclear industry. So they have to go through a acceptance process. It takes years and years. Probably some of them are in these processes currently. For the newcomer reactors, may be able to use these practices in their processes. And also not only this kind of manufacturing processes, but also new materials should go through the screening process in order to accept it in the industry. There are challenges. These are economic challenges in order to make the new reactor designs competitive, cost competitive with other nuclear and also other energy generators, especially renewables, so that this one is important item. Capability challenges, quality challenges, these are usually important for companies. So their manufacturing capabilities, design capabilities, they have to develop some new capabilities in order to compete in the market. Especially quality is important challenge. Otherwise, if there are some faulty material that would not easily accepted, and that would create important damage in the company's operations. Safety culture. This is a relatively new concept, but widely disseminated in the industry. Every person working in the supply chain should have proper safety culture, absorbed safety culture. So this is not only some written material in the textbooks or some other materials. The human beings should absorb that and reflect that in their operations, so that every person may create some kind of significant effect in the operation of the nuclear reactors. Obstacles and opportunities. I'm getting towards the end. There are certain different technologies currently developed in nuclear area, especially SMRs. So that's an obstacle, because every design, every technology will require different materials, different manufacturing technologies, so that supply chain companies should be diversified in order to operate in accord with the different technologies. Standardization conflicts with localization, so that standardization promote series manufacturing operations, and especially small markets may not be able to cope with that. Therefore, localization may be difficult for them. Normally, pressure vessel, for instance, takes more than 3 years to manufacture, but SMRs consider shorten that time, less than 12 months, but still that is in the progress. And also manufacturing equipment, especially for the large, heavy equipments, they require large forging presses, more than 15,000 tons in capacity. So there are a certain number of available presses in that size, but if there are significant amount of orders, that may not be sufficient, so that new installation may be required. The last item, probably the most important one, insufficient experienced human resources, so that we should start developing necessary human resources with the desired capability. Opportunities on the other side, standard design in SMRs, so that will create a positive economy. Shop-made and off-the-shelf equipment, so that we don't really consider different designs for different power plants. This will also make positive effect in the economy. modular construction, so we can put several units next to each other. New equipment and investment and installations are expected, so that there are decisions towards that item. So this is a positive sign. And certain industries, especially aerospace, defense, and transportation, including nuclear, they share their experiences in operation and safety, so that they will improve the operation characteristics of nuclear. This is a positive indicators. Is important item. This is not really pronounced widely, but most of the SMRs, newly developing SMRs, using high assay, low enriched uranium, HALEU, that covers 8 to 19% enrichment, but conventional reactors use 4 to 4.5% enrichment. This is available widely in the market, but HALEU is not. So there are certain initiatives in the world to make HALEU production, but still it will take some time, and probably reactor developers will be negotiating with enrichment companies or fuel companies in order to secure their supply for the incoming orders. Probably one of the last slides. So I just want to make some remarks about the domestic situation. So there are companies provided equipment and services to Akkuyu project, and also some other international projects, mostly non-safety related equipment. In order to be successful in the market, we need more experience, and we have to have partnership with foreign companies initially, and investment and awareness is needed. So this sector, this industry is not an easy sector, but once you get into the market with quality products, you get your rewards. So that market is enlarging, and you have to do necessary actions in order to provide some kind of awareness for your company in the market. So in the NGO side, Nuclear Engineers Society, NUCSAC, this is the cluster, nuclear industry cluster, and NİATR, Alikaan Bey mentioned about NİATR. This is the Nuclear Industry Association of Turkey. These are the prominent NGOs to promote nuclear involvement in the country currently. Of course, we need more effort in order to create more awareness in the community. And also, there are certain international programs. We are not member in that, especially Euratom. That kind of involvement will create positive results in the future. And I have one more slide, short one. For the future, nuclear manufacturing companies make additional investment for capacity increase. This is a positive sign. Strategic partnership between supply chain companies. This is a necessity. And there is an expanding market in the world. So we have to be a part of that market in the future. Thank you very much for your attention.
Okay, thanks for this very explanative presentation, dear Professor Dr. Üner Çolak. And I think there is no question anymore. Okay. Şimdi de Doktor Erol Bey, Erol Biçer'e sözü vermek istiyorum. Erol
Well,
Bey
I have
de
to leave because I have another meeting, but I would like to
okay.
listen Erol later on. Probably it will
Okay.
be a good speech.
Thank you. Thank you for
Thank
your
you.
participation. Thank you. Bye.
Bye-bye.
Erol Biçer, he's talking about the energy in the development of the infrastructure, which is resistant to the climate change, I think. Is that right?
Right, yeah, that's
So,
about right. Yeah.
yes, so Erol Biçer is a nuclear engineer, and he's working especially on the FNC Technology Limited company. So he is the manager responsible for the overseas business team. So the floor is yours, Mr. Dr. Erol Biçer. Please,
All right.
thank you.
All right, thank you very much for the introduction, and I will be quick as I can. My name is Erol Biçer. I'm a nuclear engineer. I studied in Hacettepe University. I graduated in 2013, and since then, I've been living, working, and studying in South Korea. Right now, I am working for a company called Future and Challenge Technology, and I'm a overseas business team manager in this company. And today, I will talk about the role of nuclear energy in developing climate-resilient infrastructure. So this is my agenda for today. First, I will talk a little bit about what do we mean when we say something is climate resilient, and then I will continue with the new nuclear paradigm, how things are changing for the nuclear industry. And then I will switch over to small modular reactors and some of their unique features for the climate resiliency. And then I will conclude my presentation with some remarks. So in this slide, I took this map from a website called Carbon Brief. They are updating very up-to-date information about extreme weather events that are linked to climate change. As you can see, these extreme events are heat waves, rain, flooding, drought, and storm. And all around the world, we can see they're popping up very frequently. And I think we all experienced this last summer. Everyone experienced a very extreme heat wave. Therefore, these extreme events are directly related to the climate change. And so when we talk about the climate resilience, especially for the climate resilience infrastructure, Professor Çolak a little bit mentioned about this, but we actually talk about two things. The first one is that physical systems, bridges, power stations, buildings, houses, schools that can withstand and adapt to impacts of climate change. So it has to be strong, and not just being strong, but also it has to be flexible. So to do that, of course, we need a couple of steps. So first of all, we need to do some risk assessment and planning. We need to evaluate what kind of problems are waiting for us, so that we can change our design and develop materials that can withstand these kind of extreme events. And to do that, we also have to think about these robust designs, which brings us to redundancy and then diversity. And those who are familiar with the nuclear engineering concept, diversification and redundancy are the basic fundamental nuclear safety concepts. If you look at the nuclear power stations, there are a lot of different trains, and there are a lot of different different systems that perform the same action. So it is quite actually embedded into the nuclear safety culture. And then finally, of course, these systems have to be flexible and adaptive, and that's what brings us actually to the small modular reactors, which I will talk more in detail. But before I actually go to the nuclear side, I wanted to give a couple of examples about what are some good examples of climate resilient infrastructures. And I collected 3 of them. The first one is the concept of sponge steel. And this is a great way of dealing with flooding in the case of extreme rain and in the case of downpours. What it does is it has this founding porous material. When it doesn't matter how much it rains, it just absorbs, and then with the help of channels, and it just manipulates the waterways and then make sure there's no flooding. The second one is the deep lake water cooling in Toronto. This is the middle picture that you see here. This is, I think, a very smart and very cool system. What it does is, for district cooling, instead of using the traditional methods, what they did was they put water channels at the bottom of the Toronto Lake, at the very bottom. And the reason why they put it at the bottom, it's for a very unique property of water. As some of you may know, the water is the densest at 4 degrees Celsius, about 40 degrees Fahrenheit. So at this temperature, the water is the heaviest, so it goes down. So that if you collect the water from that deep water, then it means that you are getting constant, similar regulated temperature. So it's a very, very cool system. And the last one, I think, is one of the very typical system, is the climate resilient housing. This particular house that you see here, it's built for hurricanes that collects the strong winds and hurricane power and generates power using this strong winds. So these are some of the examples, but there are a variety of applications available in the world. I want to switch over now to the nuclear side, and I think a lot of people have used this kind of slides and talk about the generation of nuclear power plants today. But I just want to mention quickly that in the beginning, the first generation nuclear power plants, these were the demonstration reactors where they were small and they were just used for demonstration of the proof of technology. And then when we switched to generation 2, we start to use some active safety systems, and then we increase the electrical power output. And we wanted to get more power and also standardized design, so therefore that led us to generation 3 and 3+ reactors. However, after Fukushima, the importance of the passive safety systems came into the light. Then we introduced the generation 3+ concepts, where they rely on more like natural phenomena to in the case of an accident. But this is still not enough, because if you look at today's light water reactors, and you can see actually this whole system, this whole giant gigawatt nuclear reactor, what it does is it just increases the temperature about 30 degrees between the inlet and outlet of the core. Therefore, we need higher temperatures and higher efficiencies. So therefore, they introduced the concept of generation 4, where we can work with higher temperatures and higher efficiencies. So today we have about 440 nuclear reactors operating worldwide, and then there are about 66 under construction. So it's about per gigawatt per reactor. So 1,000 megawatt per reactor is currently operable in the world. So this baseload large conventional nuclear power plant, they're already actually quite useful for the climate change, because first of all, they cut a lot of greenhouses during their operation. They don't emit any greenhouses during their operation, and they have a very high energy density. With a small portion of uranium, we can actually generate a lot of energy and power, and then they are reliable. Nuclear reactors have among the energy sources have the highest capacity and availability factors, and compare with the wind power plants or solar power plants, of course, the land is used more efficiently relatively. And if you look at the carbon footprint, as I mentioned, if you think about just the operation, there's actually not very, very negligible the greenhouse gas emission, but we have to look at the whole life cycle. But even if we do that, we can still see that nuclear is among the lowest ones. So you get a lot of energy, reliable energy, but also a lot of very little carbon dioxide emission or greenhouse emission. So it's a nuclear power plants, the base load nuclear power plants are already contributing the fight against the extreme events caused from the climate change. However, this was our comfort zone, the base load nuclear power plants. However, the paradigm in the nuclear energy and nuclear sector is changing to a more challenging way, to a more demand-leading way, because we don't just want to produce electricity, but we want to use these high temperatures and for other applications. And then another important part is we have to harmonize this technology with the renewables. And a lot of renewable folks, they badmouth nuclear, but the nuclear engineers mostly, they are not like that. We believe we can all do it together, and we have to work all together for innovative technologies. And to do that, the new way of doing it is it has to be safe, it has to be feasible, it has to be economic, and it has to be flexible. And the flexibility here is directly related to the resilience of the station, of the power plant, and also this is related to load following, which I will talk in a bit in the SMR reactors. The next part that I want to talk about, I selected a few climate resilient features in small modular reactors. But before, I think it's good to define the small modular reactors. General consensus is these are reactors that are smaller than 300 megawatt electric, and this is the name stands for SMR, small modular reactor. So the small is the size of the reactor, but the modularity comes from two parts. One is the construction of the modularity, and then the other one is the modular design of different parts of the reactor, or the entire reactor is being installed all together, such as NuScale and other type of reactors are combined together. And this SMR category, there's also one special subsection, what we call is the micro modular reactors, or Americans call it the micro reactors. They are even smaller version. They're about less than 10 megawatt electric. I will talk a little bit more about them in the upcoming slides as well. And one of the most important parts of the SMR reactors is the cogeneration capabilities. And most of them are actually designed and potential to build for a niche application, such as the hydrogen generation and district cooling and heating, desalination, and so on and so forth. And as of October 2024, IAEA declared that there are about 70 SMR designs, but we can increase this number up to 100 because there are a lot of very early conceptual designs of these SMRs and MMRs that are often just ignored. And I want to talk a little bit about these advantages of SMRs, but specifically for the climate resilience part. First of all, these are small reactors, so they have a smaller source term, meaning that their core is small. Therefore, they have a lower, what we call the core damage frequency. Core damage frequency is a metric that we use to assess the likelihood of a severe accident in the lifespan of these reactors. And in the baseload power plants, this ratio is about 1 severe accident per 20,000 years of reactor operation. But in small modular reactors, this is much lower, and 2 or 3 orders of magnitude lower. And the second one is the flexible operation. As I mentioned, the load following. So as you may know, the nuclear reactors are not just turn on and off type of power stations. So in the coal power plants, you may stop burning coal and then just follow the load, that the demand for the electricity, so you can turn on and off. However, in nuclear reactors, if you turn it off, that the amount of money that you save from not burning uranium in the core is not corresponding well enough to the amount of thermal and mechanical stress that you put in the reactor system when you decrease the temperature. So baseload nuclear power plants, we don't want to turn them on and off, so they're not quite flexible. But small modular reactors, as I mentioned earlier, we can connect them with other systems such as district heating and cooling. Therefore, we can do load following operation with this sort. And I talked about the landscape that it occupies in nuclear power plants. Base loads are about especially for the emergency prepare zone, we call it EPZ. That's the zone, the periphery that we have to evacuate in the likelihood of a reactor radioactive release. And in nuclear power plant, that's about a 1 kilometer radius. But in small modular reactors, they're about 300 meters, so it's much lower. And I already talked about the electric and non-electric applications of SMRs, and I will also talk about the potential connection with the renewable parts as well. So as for the microreactors, as I mentioned, these are also not very new. American military has built so many of them, but they were not very cost effective. So they are just built in a factory. They can be shipped with the current means of transportation, like a trolley or a truck or a train, and then they're mostly self-regulating. And their attributes for the climate resilience as well, also they are also very quick to deploy, and assuming that they are operable, they are quick to deploy and then start generating energy wherever they are installed. And you can take these to remote areas. For example, during a disaster last year in February, when we had the earthquake in the Hatay region of Turkey, we could have deployed these modular microreactors there, and then just we could light up the entire city. Or we can use these kind of microreactors in the military installations, or in also Cyprus as well. So I just want to mention a couple of important passive safety systems for regarding the climate resiliency. I think a lot of people talked about, and then I know Thoroton talked about molten salt reactors. So this is a typical molten salt reactor configuration. As you can see, this is the primary loop. The molten salt with the fuel is flowing in here. So in the case of an accident, there's something here we call the freeze plug. This is actively cooled, and in the case of an accident, this freeze plug, let's say there's a loss of power in the station, and this freeze plug is melted, and now this channel is open. So the fuel automatically, naturally, with the gravity, it will flow and fill these emergency drain tanks. So once they flow in there, the criticality will go. It will be subcritical. The fission reactor will stop, so that it will not generate any more power. So it's inherently safe just by the design. Another one that we can say, I talked about efficiency and higher temperature, and then these type of new fuels, they're not new. They were, as Professor Çolak said, the idea is not new, but the technology development is being progressed. Using the TRISO fuel, these are very small, tiny fuel kernels and particles that can be embedded into pebbles or prisms, cylindrical prisms like that. And then they have sort of their own containment. So in the case of they can go very high temperatures, and in the case of an accident, you don't need an extra containment to contain these fuel kernels. And in America, there's a lot of efforts to manufacture this kind of fuel. And I mentioned about the compatibility with the renewable resources and the load following. So this chart shows two of these systems. One of them is the TESS, thermal energy storage, and the other one is the NHRES, which stands for nuclear renewable hybrid energy systems. So when we have a nuclear reactor here, and then we can generate power and send it to transmission, no problem. We can generate electricity. But if we don't need that electricity, then what we can do, instead of sending the hot steam to the turbine, we can send it to a thermal energy storage system, and then we can utilize that as an industrial heating. Or we can use that hot steam for the production of hydrogen, for example. Additionally, these systems can all be interconnected, and then we can get the maximum efficiency, especially for the flexibility of small modular reactors, enable us for these kind of systems. And as for the concluding remarks, I looked to Turkey a little bit. By 2023, we were expecting to have reach our installed capacity to 125 gigawatt, but we're now closing 2024, and it's around 114 gigawatt right now. So we are missing about 10 gigawatt, which means 2 Akkuyu nuclear power plant, 8 units of 1200 VVER reactors. So we need more energy. And as you can see, the using of coal is increased a little bit, even though there's a lot of efforts for the solar power plant, but it is just not enough. So we need more energy. And then we have to make a very comprehensive plan and a target depending on what kind of SMRs that we will need in the future for what application, because as you can see in this figure on the left-hand side, the exit temperature of SMRs are different. So we have to target pinpoint specific reactor types. And then by doing that, we can also, of course, fulfill the European Union's expectations for decarbonization. And then if we follow the infrastructure requirements of IAEA, which we must, there's 19 of them, and then one of them is the environmental protection, that we have to work with the environmental issues as well. So to conclude my presentation, I mentioned that SMRs have a lot of potential for scalability, and then they are increasing the safety with the advanced passive safety features, and also they can be integrated into renewable and other energy sources, which allow us to adapt and flexible operations during climate crisis. Lastly, what I want to say is that this is not a one-man job. It's sort of a all hands on deck situation. So all efforts must come together for reducing these greenhouse gas emissions, and so that we can succeed our common goals. So yeah, thank you very much for listening to me. These are our company details, and if you have any questions, I'm happy to answer.
Okay, thank you very much, Dr. Erol Biçer, for this very descriptive and comprehensive presentation. I think there are no questions anymore. So if you also don't have anything to say anymore, so I'm now able to close this session, and I wish good success to everybody. And now this is the end of our session, and have a good evening. Thank you.
Thank you very much.
Bye-bye.
Bye.